All right, so we're going to kind of free form here on the last session, the panel session. We've kind of tried to get representatives from the different levels of the deep, murky ocean up here. Um, and we had a few questions submitted ahead of time, and we're willing, obviously, to take questions here as well. We're just going to kind of ping pong. So if we still have a mic for people to, uh, yeah, from the audience to ask questions. So at this point, anything is fair game now that you've heard all of these presentations. Maybe there's some cross-pollination questions you want to ask. And if you want to ask a question, feel free to direct it at any of the folks up here. And we'll just try to have fun with it and see what you're all interested in. Okay? All right. So I'm going to start with a pre-submitted question to kind of get things warmed up here. And this one is languages succeed in large part in large part because of the ecosystem of libraries they have. So languages in general. How can shading languages catch up in this regard? So you want to take a crack at that one, Ben?
Sure. So I have yeah. So when I was brand new at Unity, I went to a trade show. I think it was the Game Developers Conference. And I was at the Unity booth and somebody came up and I said, "So do you use Shader Graph?" And he said, "No, I use," and it was like our main competitor. And I was like, "Oh, well, why is that?" And he said, "Because they have examples." And I really took that to heart. And so I spent the next, like, as long as I was at the company, making examples. I think there are a lot of things that you can do to make your language more successful. I would start with making cool samples that attract attention and kind of suck people in. And once they're in, you want to reduce friction. So you want to do things like in my case, making libraries of subgraphs so people don't have to reinvent the wheel, or code libraries. Making example shaders, example code that people can draw from. You want to try to make it as easy as possible for them to use and just remove barriers, just like improve the documentation, those kinds of things.
Okay. Jesse, did you want to weigh in on this one too?
Yeah, I mean, I like that. I like that a lot. I also, well, I guess this is almost more of a challenge than something that's conducive. But one of the things that I find is the biggest challenge in working with at least the shaders that I see authored around Unity are getting them to work everywhere, which is another piece, because there's things like data types that work better on one platform versus another, or even arithmetic operations that work better on one platform versus another. On the CPU side, I think the classic version of this is implement memcopy, right? It really depends on the architecture you're targeting, and I wish I had a solution for this. It's something that we've tried to solve with things like data type abstractions, where we kind of make low-level substitutions when we do the final reduction of the instruction set. But that's not something that's available to just everybody, I guess. So yeah, I'm afraid that's more of an unsolved problem than a help. But yeah, I like Ben's idea of the toolbox. I think all of us as coders kind of keep that little section of handy routines around that we like to bring out and use every now and again.
Okay.
And I just kind of want to point out that the folks from Weasel were just up here showing you a package management system that they've built for their ecosystem. So I think at least some of the languages are trying to reduce the barriers between sharing that code as much as possible. From the Slang perspective, we're adding things to our kind of core module library. But something crazy like Rust crates are kind of like the end goal of where I'd like to end up.
Okay.
I would just want to throw out one of the challenges I see in this space too, is actually so as we're trying to test the HLSL compiler, we've come up against the problem that there's very little HLSL that is public. And so the challenge that I'm going to throw out to all of you who actually write this code is to think about how much of your code you could make public, and if there's ways that you can make things public. Because I think one of the barriers to getting good libraries for people is getting code public that can be slurped into libraries. Because I'm not a rendering engineer. I'm not going to write rendering engineering algorithms. Like, I'm just not. Like, that's not my ability. But if someone else writes an algorithm in HLSL somewhere that I can pull into a library, like, then there's a lot more you could do. And I think that probably stands across all of the languages, regardless of which tools you're using.
Yeah, I think in terms of like shipping libraries, there's some limitations of like composability in the shading languages and in SPIR-V. And as language designers and SPIR-V developers, like I think there was clear demand from this audience at least that like we need to keep pushing and make those things better so that they have like better things to target.
Okay, great. How about from the audience? Do we have a topic that anybody wants to explore? All right.
Is this on? GPU function calls.
Op function call. I know what you mean. Yeah, there's like even within that there's like various levels and kind of scopes of what that could mean, and each of those has unique challenges, right? Like work graphs is one thing. Being able to like compile slang modules separately and then link them and have that be a fast link is a different thing. And these all have challenges, and they're all going to take a lot of engineering work. And I think that they are in our future, but it's like we're getting there, and it's going to take some time to get there.
I just would add that, like, I think that people who write a lot of CPU code think that something like a function call is a very simple thing because you kind of take them for granted. Virtual functions are, oh, sure, whatever. Like, we do them all the time, right? It is very different to implement something like that on a GPU. There's a radically different, model for how performance works. And while I think it is unbelievably impressive how much of C++ CUDA makes work on a GPU. I think anyone who's done a fair amount of CUDA programming can also tell you that that's a really good way to blow your foot off with a shotgun, because that's like, a lot of things in C++ can't be lowered efficiently to a GPU. And so, like, there is a balance there. It's an even harder balance when you take into the account the fact that it's not just one GPU vendor we need to care about. All of our ecosystems care about a lot of different vendors, with a lot of different GPU hardware. And like, I know Spencer was talking about the no inline hint that we have in SPIR-V. Like, there's a reason it's a hint, and that reason is because some hardware vendors can't not do it.
So I raised this in personally, but I think it bears repeating. I think this is all true, but this also kind of stands in tension to the idea of Vulkan being, say, an explicit API. I think in something like Vulkan, if you have the opportunity to do something like a function calls, you should be able to take the responsibility of making the decision. I want to pay for the interaction. I want to pay for potentially the cost of implementing it correctly with regards to divergence and whatnot. At the end of the day, I believe there's a place for them. I'm not saying, you should do every call should be an indirect function calls on every vendor tomorrow. What I am saying is anything towards more dynamism, more interaction in shaders is something I'm greatly looking forward to.
Well, the next question on the list kind of goes into that one a little bit more. Should we ditch HLSL and go all in on C++? Maybe we can.
I will say this for everyone here all at once. I've said this a few times to a few individuals in the audience here separately. There are certain language features in C++ that I will fight to the death to keep out of HLSL. The virtual keyword, the exceptions, like there are features of C++ that I just do not believe belong in a shading language. That said, we are moving HLSL closer to C++. There's certainly opportunity for us to take some of the things that work well on GPUs and bring them into C++. Like I think that would be really cool. I think that if you want to use C++ to write shaders, you're a lot braver than I am.
Yeah, and I'll weigh in on this too. There's a lot of perhaps tension in the environment today. There's people that think that domain-specific languages are the thing for lots of what we need to do going forward. Boutique languages that do exactly what you want to be done in a certain situation, and then Khronos is the embodiment of let's make things standard so we only have one thing that everybody can agree on. And I think what we've seen here last couple of days is there are a lot of reasons why there are different languages. There are a lot of different constituencies that require different things. And in my talk, I was talking about the translation of human intention into machine execution. And there are a lot of different humans with a lot of different needs, and that ends up causing us to have multiple different solutions. Now, I think we can always go back to the basics and ask ourselves, what should we focus on here in terms of doing that translation from human intention? We got into that a little bit with the last couple of presentations here, talking about the artists and how the artists think. But this whole area is about translation from the imagination all the way down to the hardware bits and bytes, and a lot of different ways to do things there. So no one right answer yet, but let's keep looking for it. Yeah, let's go back. We got a question in the back row there, I think. A couple. We'll maybe hit a couple here.
So it occurs to me, not just in the last 2 days, but over the course of the week, game developers have received a lot of attention. But what about movie makers, people doing animated content, more for entertainment and less for interaction? Curious about do they need different things than game developers, and if so, can you speak to those things and what we might be doing about them?
Yeah, so basically, if you don't have a real-time interaction requirement, does that change the requirements for the shading language? Is that kind of what you're asking?
One of the things that I didn't get to ask Chris, who spoke about OSL, is what is the priority in that language? Is it speed or is it image quality, right? Because if you're creating a language for games, your number one priority has to be speed. But if it's targeting film, it has to be image quality. We talk about film and game graphics coming closer and closer together, but that difference in priority will make it so they can never be the same. So if you have a language like OSL that's specifically for film rendering, I don't have experience using it, but I believe that it has to have as its number one priority image quality, and speed is secondary.
Yeah, and it may have a different speed versus developer productivity trade-off than games do. And so like Hugo's thing, like let's have function calls. Like maybe they want function calls and they don't care if it's 5-10% slower. That could be just fine.
And my experience too, it's always seemed like there's a hard line when it comes to, is it interactive? Like, is it 30 frames a second or whatever the nominal rate is for when someone is dissatisfied with the performance. And so things fall on one side of that line or the other. If it doesn't require real time, then you can do much more. You can take your time, you can do it the right way, whatever. But if it has to be underneath the line of real time, then you take all the tricks and hacks that you can do to get under that. And over time we've seen that happening with hardware, that once things make it into hardware and get accelerated, then all of a sudden, okay, now we can do that. Now we can include it in these languages. But until that time, it's not necessary.
I was thinking actually, as a couple of the other folks were we're talking about this. We also had earlier in the week, for those that were here for Vulcanized, there was a talk from I think it was from Autodesk, and it's exactly that trade-off. They're like 10 FPS is fine for us because what they care about is the absolute reality of the solution, and that's not a trade-off that everybody, or it's a different trade-off than a lot of people will make, especially if you're doing games or something like that.
Yeah. Okay, did we have another one in the back there? Oh, we've got several popping up here. We'll see if your questions are better than the ones I got here.
No promises. How do you see the AI coding agents affecting the various ecosystems over the next, say, 2 years or so?
Go ahead.
So I not this past weekend, but the weekend before, was at FOSDEM and spent. If you're not familiar, it's a big open source conference in Europe. And I spent a lot of time in the AI plumbers room. And I know that both there and in the main track of FOSDEM, there was a lot of discussion of the sudden influx of AI authored PRs to open source projects and how it was really putting a strain on the reviewers and the maintainers because you cannot keep up with the machine, but it's incumbent upon the maintainers to make sure that everything that lands is actually something that they want to be a part of their project. So as far as where we're going to end up with it, I'm not sure that I have a great answer, but I think that we're kind of in the middle of a period of learning and negotiation about what the interface between us and the agents looks like. And I think it's going to take us some iteration to get it right.
My slightly snarky answer is we've heard a lot here this week about how challenging GPU debugging is, and GPU debugging somebody else's code is not easier than that. So that's kind of at the moment where I'm at with it. I'm not saying it won't get better, but yeah, I think it's and Shannon's also highlighting a huge knock-on effect, which is, okay, so you've got all these PRs coming in, who's reviewing them, who's running them through continuous integration, and who, it turns out you need to amplify a lot of parts of the process before you can get everything, moving smoothly through the system.
I will say that people who know me will find it very skeptical that I'm going to say this in all earnestness, because I generally do not look favorably on a lot of the AI stuff. But what I would actually say is to Ben's last talk, I've worked on noodle graphs before. Noodle graphs have actually not the shallowest learning curve. There is another world, though, where artists could actually get the visual effects that they want by iterating with an LLM. And I think that actually could be a very powerful way to bring people who can't reason about even a noodle graph necessarily into a creative process. Now, I wouldn't want to debug that code. I would not want to integrate that code into an open source code base because it would terrify me. But I do think that I use LLMs to write throwaway Python scripts all the time, and I could absolutely see myself using an LLM to write a throwaway shader that did some visual effect that I wanted to see, just to see it, to be able to see what it does. And so that actually, I think, is a really powerful thing that we could see in the vaguely near future.
So a couple of weeks ago, I had somebody leave a comment on one of my YouTube videos, and he said, "You're not implementing this in the most optimized ways." I was blending terrain layers together, and he said, if your layer mask is black, you should branch so that you skip that layer and you don't have to sample the textures and such. And I was like, oh, that's a cool idea. And I replied, hey, I really want to try that. Can you point me to an example implementation? And he said, well, no, I'm sorry, I can't, because I just told the LLM to do it, and I don't know where in the code that it actually. And I just kind of rolled my eyes and man, what are we coming to?
So I've worked with and worked on multiple shader graph implementations. One thing that has always bugged me is they have 100,000 different functions. And whenever I go to build a new one, I cannot tell which one of these are actually used by people. Neither Unity nor Unreal would publish statistics about this. and they will always have slightly different variations of the same thing. Could we do a better job of standardizing that? Also thinking forward for things like the HLSL and slang standard libraries.
I would love to have statistics about who uses what features of HLSL. There are lots of reasons why we don't have such statistics. I would love to have such statistics, especially now as we're implementing our third compiler, because I really want to know what features I can leave behind and not implement. Hey, geometry shaders, I'm looking at you. I think that there are some features though that like probably have 0 users, and we have no way of knowing that.
As somebody who has repeatedly implemented one language over another language, and usually the language being implemented is old and crufty, I can tell you that there is almost nothing in this world that has 0 users, and the one user it has will find you, and they will be angry that you left it out.
I'll defer to Ben a little bit on this because he's technically worked on ShaderGraph more recently than I have. But when I was on the ShaderGraph team years ago, there were certain things that we couldn't remove in favor of something new because we're not really supposed to break users' code. And I'm not saying that we never do that, but we're not supposed to. So we might do a thing like add a mode to a node so that you can preserve the existing behavior for people that are relying on that, sort of bug for bug compatibility, and then add the new mode so that you can use it in a way that is either more correct or faster or whatever the new thing is supposed to be. But I hear what you're saying about it would be nice to know, like, what should I be using and why, right?
I don't know if I'm allowed to say this, but I don't work there anymore, so they can't fire me, right?
Yeah.
Unity does have statistics for how often each of the nodes is used. And I don't know if we're allowed to publish that or anything, but if that would be useful and people want it, maybe you could like go and find out about that. One of the things that we did is we generated that list, and like obviously multiply is right up there at the top, and sample texture 2D. But we had an ordered list of, these are all of the nodes in the library ordered by how frequently they're used in the graph. And internally, that was super useful information for us.
All right, let me switch back to another one here. We approached debugging as a topic here a second ago, and the setup for this question is just great. So it says CPU debugging makes me feel good and brings me joy. So how are you going to bring me this joy with GPU debugging, especially shaders?
I think GPU debugging is a very different thing than CPU debugging. And even if you support single step debugging, like you set a breakpoint, it's gonna get hit 10 million times. And like how do you know, like you still have to like do things to kind of narrow in on what you actually care about. And so I don't know, I like honestly when I have to debug something, I use debug printf, and it's like on the CPU, like CPU debugging, I consider debug like printf's like kind of not the most advanced way.
The pinnacle of debugging.
But on the GPU, like, you can do like if my pixel location equals this, debug printf, and you can do all sorts of logging. And I don't know that there's necessarily a much better way that we should all be looking forward to. I'm sure Aurelio would have a different opinion, but he's not here.
I think actually, Jesse's talk highlights one of the challenges of like shader debugging in like real applications where the layers of translation get in the way. So like one of the things that and I will say we are nowhere near as good as we need to be, but like the HLSL compiler is really focusing on native compiling flows from HLSL to a target ISA that directly maps to the HLSL. And today we have experiences supported in both Clang and DXC where you can compile HLSL directly to Dixel for DirectX, SPIR-V for Vulkan, and if you call the metal shader converter direct, you can also hit metal with it. The metal shader converter has its own limitations, but it does actually preserve debug information into the HLSL source, so you can use the metal shader debugger tools to debug HLSL. And I think that is super valuable to be able to actually like write your shader in one language and see it. We, as kind of an ecosystem, have a lot more work to make that the norm, and we have a lot more work to make sure that compilers are generating good debug information that debugging tools can use and can benefit from. But it's a really hard problem.
I thought we were going to just have to say redefine pain as joy, and you'll be.
Hey, there are people that's true for.
Yeah.
And no judgment.
All right. Any other questions out here? Yeah.
Okay. This is from academia. It's a nuanced topic, but I'm going to formulate it a bit harsher than I normally would. A lot of technologies are basically unteachable. If you think about C++, Vulkan, I follow the Reddit subreddit about Vulkan, and sometimes there's a post, after 3 months, I got my first gradient triangle that shows up. Hooray. Isn't that like a bad thing for the future? That like either we have to say just start with OpenGL 1.0 with GL Vertex F to like get more quickly there, or we spend a lot of time on explaining these technologies to get students somewhere productive.
I want to, because you said one of my favorite things this week, I want to point that back at you and ask, where's that balance point between it's going to happen easily enough that you'll forget in an hour versus you spent enough time for it to really cement itself in your memory and in your thought processes.
Yeah, that person has 3 months of experience now, right?
Yeah. I honestly, I'm not being snarky about that, but I mean, there really is a balance there, right? Like that notion. I go way back with the author of the OpenGL Red Book, and he and I would talk about this a lot because the simple OpenGL program that gets you that triangle on screen, it's 5 lines of code or whatever it is, especially if you're using like a library like Glut or something to do the actual presentation. So yes, but it's, okay, now that I've done that, I don't know what else I can do with that. But if I get through, I hope it's not 3 months. Now that does sound problematic to me, but if I've spent that much time going through and understanding Vulkan to the degree that I do, now I can do a lot of other things, right? And I think you touched on this in your talk, Kuhn, and I think Spencer also, with that notion of starting with something simple like adding 2 values in a buffer and then moving on to graphics from there, and kind of building up. So it's more about finding the right progression. And maybe not reaching too far so that you don't stand a chance, right? Setting yourself up for a little bit of success.
Isn't Copilot just going to make that gradient triangle in 5 minutes? Right. No, sorry. But I want to just point out that there was a great discussion during I think it was the Vulkan panel about like sane defaults and things to help with a lot of this. So I think there's a lot of work also going on in the Vulkan working group to really think about how to make the APIs more approachable and more usable. And I think that is extremely important work. And it's gonna factor into a lot of that too.
So I've also seen the Reddit posts where someone is overjoyed 3 months after getting their first triangle on. And like on the one hand, I'm happy that they're overjoyed. It also makes me kind of sad. It shouldn't be that way. But I think we have to recognize that no API is going to be for all audiences. Like there's been some stuff that we have seen both in Vulkanized and here in the Shader Symposium, like the stuff, the WESL stuff, like that was really slick, really low cost of entry, very accessible. Stuff like that is a great introduction. WebGPU is a very attractable introduction. I also said at the very start of Vulkanized in my first talk, like we built Vulkan for a certain audience with a certain set of constraints. And part of me thinks maybe Vulkan isn't the right thing to try to teach to students first. Like, there are more accessible things. We're never going to hit everyone. And I think you can apply the same thing to shading languages as well. Like, is HLSL the most approachable shading language? And I'm not picking on HLSL over GLSL, like either of them. Like, they require a certain level of expertise compared to shader graphs. I think you have to choose your audiences and build for that, which was like also a talk we've had today.
I'll just own up to the fact that HLSL confuses people with decades of C++ experience. So like, it is definitely not for the faint of heart. Like, and I'm impressed when we're teaching students how to use it.
And I think you can level the same criticism as C++ as well. Like, when I sat through your talk about like doing a C++ shading language to remove the load of expecting students to take on two things. Like, on the one hand, I really bought the argument of like, this is one less thing to talk about. On the other hand, it's like, now we're just making them deal with one really hard thing. And like, could we have done better by making them deal with two approachable things? I don't know.
And also, I think there's a difference between, like, you could write a super simple shader and wrestle with the graphics API, or you could go and try to, I don't know, I would still recommend something like ShaderToy, both because it gives you immediate response in the window, but also because it's a broad community. There's a ton of sample shaders in there, and you can kind of go and understand how different effects work. So, I guess there's, sort of slightly different ways to kind of approach the problem as well.
I think it might be helpful for me to share my experience learning these things. I had a friend who was in graduate school, and he came to me and he said, I think I'm probably going to end up being a professor because a lot of PhDs are. And he said, but I don't know how to teach very well. Can I teach you how to program in C? And I was just like, holy cow, of course you can. And we made this trade. Like, he would come once a week and teach me, and I would babysit his kids once a month so he could go on a date with his wife. And it was a great trade. And brilliantly, he started me out with a ray tracer because it was graphics that I was interested in. And he took away all of the roadblocks, like things like, writing out to an image file format or stuff. Like, he did that for me. But the actual graphics math, we kind of walked through a week at a time. And after 6 months of these C tutorials, I was able to take what he had taught me, and I started looking at HLSL code, and I could read it and understand what was happening. And so from that point, I just grabbed other people's pre-made shaders and just started poking them a little bit, changing this a little bit, changing that to see what would happen. And just kind of slowly, step by step, I built up to understanding. So that was my whole journey from starting. And I'm not an engineer at all. Like, I know a little bit of C and Python and HLSL, and that's about it. Sorry.
To jump back into the commentary about the learning experience of Vulkan as a first API, I actually gave this a try. So I taught a seminar to 12 students last semester where they had to implement various rendering techniques on top of a Vulkan framework that I prepared for them. And the requirement for that course was they had to have passed our Introduction to Computer Graphics lecture, which is strictly offline rendering. So these people are familiar with, your triangle intersections, your BVHs, your whatnot, but they have not worked with the graphics pipeline. And I was my students did well. They had good results, and almost all of them passed. But that led to some interesting discussions with my colleagues. And one of them was my colleague Matthias. He asked me, "Well, what are you even trying to teach? Are you trying to teach graphics, or are you trying to teach GPUs?" And I had to pause because I don't think we bother to make the distinction between these two things. We kind of conflate them, and this is true for. I think it's very obviously true with something like Vulkan or, let's say, even Web GPU. It's kind of in the name. You're programming a GPU. It's a GPU programming model after all, even though it's graphics. But it's also true for shaders. The way you think about the binding model, the way you think about what's allowed or not allowed in a shader. Whether the question of function pointers. The argumentation is. Performance always leaks its way back into it, And I guess what I'm looking for teaching, maybe I want something where we don't allow this leakiness of performance back into the minds of the users. We just want to do graphics, we just want to do shading, and we want to focus on modeling the problem and the data flow. And we leave performance for a later stage when we really try and get to something that's more what you would get to practices that are more aligned with what you find in industry, not necessarily teaching. Maybe these things don't have to be the same thing.
So I really like Ben's, what's it called, the water sailing thing. And then I kind of take Randy's original like history lessons. And I almost think like, if you look back, OpenGL 1.0, there was just hardware architects and like maybe driver engineers. There was no programming language. And then we added programming languages. And then we added engines. And then we added nodes. I mean, maybe the next evolution, maybe there's another level one day where it's just there's like talk about how to get your AI to make better nodes. But that's it. But that's another layer now. We just make another layer on top of that. So maybe the reality is we've just created many layers, and each one is hard and each one is its own domain. And we obviously have experts of like different domains of these layers on the panel now. So to me, that's just the reality.
There is no problem in computer science that cannot be solved with another layer of abstraction.
And each of these layers have their own problems. Like I could talk all day about all the issues with SPIR-V, but then there's like probably an entire community that needs to fix all the node graphing, UIs out there. There's probably just every domain has, a worthwhile time of things to do.
So I'm going to channel my best perception of what I think your boss would be saying if she were here right now, which is that like, I understand where you're coming from there, Spencer, but I think like fundamentally one of the challenges that I think we all should acknowledge is that processors are not getting smaller faster, and at some point they're going to stop getting smaller, right? Like the die shrinks are running out, and I know we've been talking for like 2 decades about the death of Moore's law, but like it is like very real that at some point, not that far in the future, like we're talking about insulators in the size of atoms, okay? And that is going to make it so that we can't just keep adding layers of abstraction. At some level, we actually just have to get more efficient. And at some level, we have to figure out ways to not just like, so like one of the things that I think a lot about in HLSL is there's a lot of undefined behavior. There's a lot of weirdness, and figuring out how we can regularize things and how we can streamline things. That will make it so that the next layers that sit on top of us, can fulfill, Jesse's goal of write once, run everywhere, and have it actually work. And I think like we need to be figuring out the layers that we have. How do we make them more efficient? How do we make them more productive? And we probably should look critically if we have the right number of layers or if we should have fewer, and where we can have fewer.
Yeah, that I think is exactly one of the points I was trying to make when I was talking as well, that if you think about it, you have this immensely difficult translation problem. You're trying to translate from human imagination to things that run on processors. And so since that's such a huge problem, we've got all these layers of things to tackle a piece of it. And if we step back at it at this point in time and say, what's the minimum number of layers we could get by with? Maybe we could make some of these things easier, at least for a subdomain of the interest areas.
I would also argue that if from a pure engineering perspective, you took 4 steps back and decided you were going to rebuild some of the high-level interactions that we have today from scratch, top to bottom, nobody would build some of the systems that we've built. Like nobody would create these things intentionally. Like we have a lot of organic evolution that got us where we are. And I think there's always an opportunity to take a step back and look and think like, is this where we want to be? And how do we get it better?
In fact, it's kind of the question I've been asking myself lately too, is hardware is hard, right? It's physical stuff, and yet we keep innovating in hardware, and software is completely malleable. You can make software do anything you want, and yet software languages and APIs have lasted for 25 years or 30 years. And I talked to Hugo, and he's buying hardware from 25 years ago because it's a collector's item, right? And yet we still have the same some of the same APIs and shading languages. So it's also a question, I guess, of how often could we reinvent or should we reinvent on the software side. It just ends up being so much stuff built on top of the software that you can't change it, or you'll break.
Yeah, but
break everybody's stuff.
those things haven't stood still though, right? Like HLSL today is very different than whatever the precursor of HLSL was 25 years ago, and I think that like incremental change in the software is very important. It's very hard to say like let's throw away, you know, throw away OpenGL and do Vulkan, for example. Like that was a very big it was a big risk, really. I think there was a chance that like we killed OpenGL and we killed Vulkan, right? Like that very well could have happened. And it's understandable that a lot of projects don't want to like do rewrites from scratch. Chris has experience. It is very, very difficult, and that's not even from scratch. It's building on top of another code base. Like it's very challenging to make very big steps like that.
Yeah, and if you'll all remember, Jesse said that they're still using FXC. FXC has not been the primary recommended HLSL compiler for almost a decade. Okay, like I think, and it's crazy for me to say this, but like I actually think like we do have a path where we will be able to replace DXC with Clang significantly sooner than we will be able to replace FXC and migrate users off of FXC permanently. The longer things are in an ecosystem, the harder it is to move things off. The more load-bearing software depends on them. And that's, part of my point of like, if we started from a clean slate, we probably never would have built all this, but we're not in a clean slate. And so.
Yeah. I mean, and a little bit to Jeff's point as well, like the head and the tail are always much longer than you would ever want to give them credit for. Right. I think about that, because it was a big deal to decide to do Vulkan because we kind of knew it would be basically declaring OpenGL, at least stagnant, if not dead. But it's still taken all this time. I forget if it was Ralph or Ian during the Vulkanized section of the week presenting like the sort of the kind of numbers as we've seen the growth of Vulkan on certain platforms, and it's not it's not like it's 100% on the platforms that support it, and we're more than 10 years in. So it takes a minute to get up there, and now you're there, and it's also we've sort of over convoluted it at the same time, and it's tough. It's I still come back to the analogy that I mentioned of rebuilding the engine while you're going down the highway. It's sometimes that's kind of the only option because you can't destabilize the ecosystem, or at least most of the time you can't.
All right. Let me do one more here quick, and then we'll come back to the audience and see if there's more. This is fairly straightforward, probably Shannon and Jeff. When will Slang be full featured for Vulkan?
I think the primary answer to that is, what do you mean by full featured? Because like definitely you saw Nia's presentation, Slang had everything that the NB Pro samples needed, and Slang is definitely as full featured as it needs to be to do an awful lot of use cases. It is out there in production. The Source 2 engine, I believe at this point is all Slang. So it's definitely full featured in that respect, but I'd also say like Vulkan is a moving target. So if what you mean by full featured is it has this one particular vendor extension that I need, or I need to be able to do this one particular use case that isn't quite working yet, what I would say to that is, please tell us, come and let us know about the features that you need to use. And, even better, if you like, you can submit a PR to add the feature to the language, because the language is entirely open source. But But yeah, I would say my response is both. It is full featured, and it can never be full featured. So
My response is when will Vulkan be full featured for slang? Right, like slang wants to do all these really cool advanced language things, and meanwhile, SPIR-V is like, well, we can't really like pass pointers as function arguments, and it has all these like weird limitations that at the high level language you're just like, this is insane. Like, why like so I think they're both moving, they're staying in sync reasonably well. So I think there's always more to do, but I think it's in a good trajectory.
So now that we have 25 years of history and we carrying all this luggage with us, especially for mobile devices, super challenging to support all this old stuff, OpenGL. So maybe just a time for prediction from all your experts in the industry. When are we going to be ready for a full reboot? Like throwaway, fixed function graphics, everything's fully differentiable, all compute, maybe all single source languages. No need to do even graphics language anymore. When are we going to be ready? What's your prediction?
Who wants to start on that one?
I fully expect I'll be retired before we're there. But what I will say, like, one of the things that I'm excited about when I look at the direction that we're moving with HLSL is that we are moving to a world where the same compiler that many of you use for your CPU code will be the same compiler that you can use for your GPU code. And I think sharing that compiler infrastructure is going to be really powerful. And like, there are some really cool single source GPU programming models that are out there. There's a lot of I'm going to plug the Fortran compiler because Fortran has done some really fascinating work on single source GPU CPU programming, which is mind-boggling but awesome. I think like there's a lot going on. I feel like when I first worked on GPU compilers, now close to 15 years ago, we thought that all the fixed function hardware was going to go away like imminently. Like we all really were like, oh yeah, we're just a few years away from your vertex and pixel shaders are really just going to be compute shaders. We're not there. I don't know that I actually believe that we're going to be there anytime soon. I think there's a lot of reason why the fixed function hardware keeps staying around.
I just have to give you props for managing to bring up Fortran in a question about when we'd be able to leave things behind. So just props.
Yeah, and getting back to what Shannon was saying earlier, there's always going to be one person, right? One customer that you have to support, and so you can't get rid of it. So I'll take that angle and say it's never going to happen. I actually gave a talk quite a long time ago, probably 2006 or so, and my premise was that I was going to predict when ray tracing was going to take over for polygon rendering, and we're well past the time when I thought that was going to happen. So the power of the status quo is just like, it's unbelievable. You've got this stuff that works and you don't want to change it, and you have to support it. The companies that depend on customers to make money have to support their customers. So this stuff always has a much longer lifetime than you think.
And I think like to migrate existing applications to a totally new paradigm, like you have, not to make fun of myself here, but like you have to add an abstraction layer that virtualizes it. Like otherwise you leave these massive swaths of existing content and existing users behind. And I think the problem that we're gonna have comes back to what I was saying about die shrinks. Like I don't know that we have enough die shrinks left to be able to have hardware fast enough that's going to emulate all this fixed function hardware. I don't know. I don't know that we are. I'm not an electrical engineer. I'm not a computer engineer, but I don't see it.
I also kind of have to ask, like, which thing is it that we're getting rid of, and what's the unified future? Because, like, are we talking about ALUs? Are we talking about tensor cores? Are we talking about, there's a bunch of different things that you could see as the one true thing in the future that everything's going to be on. So, I think, like, even now, some of the different shading languages are kind of converging on different things, like not together, but on different things for different goals. So,
I mean, like, I was thinking that there are, at least when I last worked for a hardware company, that there were just things that were too efficient as a fixed function block to do as a programmable block, and you couldn't afford to spend the power to give that up. So, I mean, I don't know if rasterizer is a good example, or if there are other things that are a better example. But, like, if you're going to do rasterization, like, are you going to do that programmably in the GPU, or are you going to keep a fixed function rasterizer? I don't know.
There are different ways to look at that particular instance. So depth test, for example, right? We kind of stuck with that for all these years. Well, is that really efficient to take every pixel, do a depth test, and then throw it away? How does that sound from power perspective? So yeah, what I was coming from, I guess, from mobile, we're under huge pressure to deliver something that can run graphics, say in glasses, at sub 1 watt, right? So, and the trouble is that our current pipeline is not quite conducive to this kind of stuff. I don't know what actually we need. Maybe we can do all ML or do something else, but what we have is not great. So if you just take it to, fully elemental operations and count power, everything that we need to do to run traditional graphics pipeline, we will never get there.
So on that point, though, actually, the great thing about a totally new paradigm, like a mobile device where you're trying to do rendering on a pair of glasses, you don't actually have, 60 years of history of computing to bring with you. And so, like, there is always the opportunity for in a space where you're building something completely new that doesn't exist. That's the space where you can start from scratch. And maybe you don't even use any of the tools that we have. Maybe you create something completely new.
I suspect they at least want to run a browser on their glasses, and that brings, there's a bunch of baggage there.
Nobody's running JavaScript in 1 watt, right? Right? Please, people.
I guess I would quip, like, who's ready to be the next 3D labs and sacrifice themselves for the good of the industry and and see it existing in a process.
All right. I've run out of questions up here. Do we have anything else out here? Given it's Friday afternoon and some of you have been here all week, we're going to do one more question here. I'll give everybody a chance on the panel. We'll start down with Jeff. What was your biggest takeaway from the Shading Languages Symposium, or one thing that you want to reemphasize and tell people to remember?
Yeah, I was really impressed with how some of the compiler developers and shader library developers were really pushing the limits of the languages and SPIR-V. I like, they're doing things that I didn't think you could do, but it also, like, it's also like a feature request, right? Like, they shouldn't have to do that. And so I want to take some of that back to, like, the SPIR-V group and be like, hey, like, there's actual demand for this. Here's a short list of things that maybe we should consider at higher priority.
So I'm really grateful for the opportunity to come here. I think my biggest takeaway is just the like the expansion of my vision of what's out there. I've had my eyes open to a lot of things. I mentioned this already, but I had a very narrow view of what you do with a GPU, and now it's just like so much bigger thanks to listening to all of you and hearing the things that you're working on. So really appreciate it.
I don't know. At the end of a week of being here, I'm kind of having these mixed feelings of being extremely energized and also overwhelmed by the massive volume of work that we still have to do. I think a lot of the talks came up with a lot of really great ideas and feedback and things that we need to be working on. Everything from ways that we need to evolve HLSL to make some of the things that you all are doing with HLSL work better, but also, I'm nerd sniping Spencer to do some fixes in SPIR-V, and we've got like all of these things that need to be done, and it's crazy. And I will also say I'm continuously amazed by how my terrible drawing of my dog keeps showing up in other people's slides. And I guess a last parting thought that I want to leave to people here in the audience is, I think that there's a lot of ways for people who are in the audience to get involved. A lot of the people who have been presenting have been showing off things that are open source or things that are, Khronos is working on. There's a lot of ways that people can get involved. And I would encourage everyone to please, think about how much involvement you can have. As the Microsoft person here, I know I'm a little awkward, but one of the things that I will also say is I'm a great example of the fact that it takes people in organizations pushing to advocate for open source, to advocate for participating in bodies like Khronos. And if you're in an organization that isn't participating, it's really on you to do that, to push to make it happen. And I think there's a lot that we can do if we all come together and start, working together. And to that note, please, people, get involved in the SPIR working group. Like the SPIR working group is massively underrepresented from people who are representing languages and representing user bases, and it would be amazing to get more of you involved so that we can really think about like how do we need to make SPIR evolve to enable your use cases and your tools. I know I rambled a lot.
So I think my takeaway is probably going to echo Jeff's a little bit, but I'll be maybe a little bit more forward and say some of y'all are doing some really gross things with shading languages, and I love it. So there are many things that I was like, why would you? Oh, okay, all right, I'm into it now. So just thank you to everybody who showed up and showed just some really out of the box stuff, and it gives me a lot of ideas and also night terrors to bring home to the slang team.
I guess for myself, there's a lot of things, and I would echo pretty much everything everybody down the row from me has said. But I also, I am constantly blown away by the things that people come here with. But what I really love, is the breadth of the things that people are doing with it, from the independent people teaching themselves how to write shader programs or how to write Vulkan code, to people that are doing really gnarly, corner case high performance things with it. And seeing that all in one room, that for me has been incredibly enriching and makes me even just a little bit proud for having been involved in the development of some of it. So it's been amazing. Thank you all. I really appreciate it.
Yeah, and for my, I'll do two since I'm last. But the first one, the hardest class I had as a grad student was compilers, and it turned out to be the class that I loved the most. I ended up getting a career in computer graphics, but compilers has always had kind of a soft spot in my heart. And I didn't have any idea that there was this much compiler work available for people. So that the vast number of projects that are going on that involve compiler work, programming languages, et cetera, encourage youngsters to study compilers, and help beef up the industry with that, because as I was been saying now a couple of times, this huge translation problem that we have, compilers are a great tool for helping address various pieces of that. And then the last thing I heard over and over here throughout the couple of days I was here, everybody wants to get feedback on what they're doing, file the bugs, answer LunarG's survey, participate in the Discord, and yeah, the benefit of kind of this kind of an environment is you actually do get to meet people and say, hey, did you ever think about, but if you can take time to do that the rest of the year and throw out those comments and file the bugs and help make everything better, that would be my last bit of encouragement. So
I just want to add, I never took a class on compilers in college, so you don't have to go to school for this to do it. Please, like, just make some pull requests. It's great. Compilers are fun.
All right. Well, huge thanks for our panels.